What? Not scalable? Or maybe it is? Today we are explaining scalable loop antennas, including impedance matching network. They are flat, they are smaller than a half-wave dipole, and they are having special properties. We were showing examples on the channel that are working great. Two orthogonal resonance modes are receiving all polarizations of incoming signals, and the filtering properties of the loops are improving the interference resilience. We were demonstrating improved signal transmission by a number of measurements. Just as a side note, there is a design tool for 5 different loop designs. Feel free to watch the video about it. Some viewers were building the antenna for their own purpose, and I'm always happy giving useful advice. Recently, I found a very good question in the comments. Can you scale the design according to the wavelengths just by multiplying dimensions? My immediate answer was, there could be a problem with the matching network, and I referred to our tool which we developed for dimensioning. Today we are giving a comprehensive answer to the question, and we are introducing a catalog of scaled designs. In other words, designs usable for any arbitrary frequency. To understand the principle, let's go one step back. Wire antennas can be scaled. Scientific textbooks are even giving the dimensions in wavelengths only. In practice, the wire diameter is influencing the so-called electrical length. For dimensioning, a length factor A, for example 0.91 in case of thick wire, is taking this into account. Keeping the ratio of the diameter to the length constant while scaling, the electrical length and the impedance of the wire antenna are remaining the same. That is important to keep in mind. The same applies to a loop, provided we are increasing the wire and the loop diameter by the same factor. Interestingly, the electrical length of the loop is smaller than the physical circumference, whereas for the half-wave dipole it is the other way round. Our special loop antenna design is comprising an integrated impedance matching network, which is making things more complicated. So, under what conditions is the design scalable? Ideally, all impedances are remaining the same when changing the physical size of the elements. We want to find out how this is possible. In case of the wire loop antenna, the matching network is consisting of a two-wire waveguide. The equation is giving us its impedance. The variable A is the wire distance and D is the wire diameter. Fortunately, we can multiply A and D by a factor without changing the impedance, because the factor in the numerator and denominator is cancelling out. With the planar design, I initially thought that the term ln of 2 could be a problem. But in fact, the scale factor for the gap width S and the width of the conductive strips D is also cancelling out. However, be careful when building the planar loop on a substrate. Theoretically, we could scale all dimensions as before, but the effective permittivity of the substrate is usually frequency dependent. Therefore, a simple scaling with a factor cannot work here. In that case, we need to go back to the Excel tool to adapt the design for other frequencies. When building from solid material, we have to keep the ratio of the gap width S to the total width D and to the thickness T both constant. No problem when applying the same scaling factor to the three variables. If the ratio S to D is approaching the value 1, these terms are becoming large, and by neglecting this term, we are arriving at the plate line design, which is also scalable. DIY makers are recognizing the advantage of the planar and the plate design. You can easily cut the right dimensions, while with the wire design it could be difficult to find wires with the desired diameter. I'm listing the dimensions for interesting amateur radio frequencies, LoRa, positioning systems, radio astronomy and Wi-Fi. For 868 MHz, a 6-square grounding cable with a diameter of 2.76 mm is suitable. For 2.4 GHz, a 0.75 square copper cable is fine. For other frequencies, it's probably not so easy to find wires with the desired diameter, making the scalability questionable. But don't worry, our Excel tool is helping you to compute the dimensions for any wire diameter you are having. The planar design is unproblematic in this respect, since you're cutting the structure out of a piece of sheet metal anyway. The design, milled from solid material, is also unproblematic, as you can choose the dimension freely for manufacturing. Unfortunately, not every hobbyist has got a metal milling machine. Let's see, maybe we will try to realize this design later with 3D printing and a conductive foil. The band material is easy to scale as long as you can cut the required band out of a copper sheet, for example. Important dimensions are the band's width T and the gap width S. The thickness D has little influence only when it is significantly smaller than the width T. So you don't need to apply the exact thickness specified, the closest standard will do. Finally, I'm giving you the dimensions as multiples of the wavelength in case you want to calculate the antennas for any other frequency. So here they are, the scalable designs. You could find other dimensions. These are my suggestions. I hope this is answering questions about scalability, and it is motivating you to build that antenna for your own purpose. But anyway, feel free to ask any further questions in the comments. After understanding the mathematical conditions for scalability, I found more scaling options than I originally thought. The main problem with scaling to other frequencies is sourcing the right material. In case you want to take material that you're just having, you can still use the Excel tool, which we improved by the way. In one of the coming videos, we need to talk about frequency selectivity, because there are also some new insights on that. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.